be Dario LEÓN, who will speak about frequency dependence in the GW approximation. So we stress the role of the frequency part in the screening.
Thank you very much for the introduction. Yes, my name is Dario LEÓN. I am a postdoc at CNR Modena. And as David said, I will speak about the frequency dependence in the GW approximation. This is the outline of my talk. First, I will introduce, starting from the GW equation, we will get to the frequency representation, and the idea is to understand the computational complexity of the GW calculation. Then I will introduce the most commonly used method for integrating the self-energy, starting from the plasmon pole approximation. I will explain briefly its origins, the generalization, and the different implementation, and the achievement and limitation of this model. Then I will also explain another alternative full frequency approaches, like numerical integration, the real axis, the contour deformation technique, and we want to understand the computational cost compared to the previous approach. In the end, I will also introduce a new methodology that is called the multipole approximation that has been developed in Yambo. I will explain some of the main motivation, and we also want to compare its accuracy and computational cost with the previous methods. Then, starting from the GW side, this is the hidden pentagon of the equation. As already the previous speaker from yesterday explained very well, in the GW approximation, we neglect the vector correction to get this simplified cycle of equation. The starting point is usually a simple approach like DFT, so we start by Cone-Sham G0. So the self-energy is null, and then the first iteration, we need to compute this, the polarizability at the independent particle level, then the reducible one, and then the self-energy, that is this product of the Green function and the screening potential W. Then how to arrive to the frequency space? We simply, I recall this picture of the Green function that represents transition of electron or holes from a given position at a given time to a different coordinates. Then, so this notation is very compact. Here I am putting the coordinates 1 or 2 represent these coordinates both in space and time. Then I will just use the time variable to arrive to then perform the frequency, the Fourier transform to arrive to the frequency space. Since we have a simple product of two operators, this results in a convolution in the frequency space. Both for the polarizability, there is a convolution between the two Green functions evaluated at different frequencies, and the self-energy. So this is the problem, the integral we want to solve for in the GW approximation. Then, as already introduced Pedro yesterday, we can arrive to a Lehmann representation. So here, this is an example I took from the book of Stefanucci. So for instance, we take the retarded Green function. This is expressed the theta function in time. We have a Hamiltonian. Then we just simply Fourier transform this Green function. We use this expression for the Heaviside function. And then we arrive to this equation here. Then if we introduce a complete set of eigenstate for the Hamiltonian, we get the Lehmann representation. So we have poles in the excitation energies of the system. Then from the Lehmann representation of the Green function, we can compute that starting from Cone-Sham basis set. So here again the poles are in the excitation energy. Then we have also the projector of the states. We can integrate the convolution I showed in the previous slide for the polarizability, and we arrive to a Lehmann representation for this other operator, where it's a very similar expression. Now we have poles instead of the excitation energy, we have poles in the transition energy. So this delta E corresponds to different state transition between state K, I, and K minus Q, J. So this is the full expression of this polarizability. In all the variables, we have used also the Fourier transform of the spatial coordinates in a crystal. So we have also symmetry. This results in G prime, and also Q coordinates. And then this object enters in the Dyson equation. There is a nonlinear equation, and we obtain the reducible polarizability. So we want to understand what happened in this Dyson equation. So we start by a representation that is we have a lot of peaks, delta-like peaks are in the excitation energies, but then this somehow this picture is destroyed because what we want is we want to describe collective excitation. We are switching on the interaction. So this picture is destroyed for the reduced polarizability. What we can do is to compute this subject at each frequency at the time. We can compute it numerically. So the computational cost of the evaluation of this polarizability can be found in this paper, for instance. So we have let's say we have an integration over the Billiard zone. We have summation over conduction and valence bands, and also C is the number of plane waves of the basis set. Then there is also a crucial point, that is the method we use to integrate the self-energy. This, for instance, will determine the number of frequencies we need to use for evaluating the polarizability. And there is also a further sum over bands in this integration. You can see the full expression in the Yambo cheat sheet, and also in the next presentation by Alberto Guandalini. So the origin of the plasmon polar approximation came from the study of the electronic correlation effect in simple metal that can be modeled by a simple electron gas. For instance, we can take aluminum as an example. Here we realize that the relevant excitation for small q correspond to a strong peak in the imaginary part of the screen potential that have a very small width. So the idea is to model this excitation with a simple delta-like peak, as I'm showing here. So we have simply this pole. This is the imaginary part. And the further application of this model has been used for the description of the main longitudinal plasmon mode observed in Ilse experiments. Here I am showing a simple comparison of this plasmon in Hartree for a set of material. We can see that is in very good agreement with the experimental value. Then this model has been generalized to the full metrics. So we are extending the model also for G prime and Q coordinates. So this is less. This has been done by Harvesting and Louis. This model is less accurate for large G vectors. So we don't have any more a single peak. We have many more peaks, but so this is less accurate. But in general, W is dominated by the small value of Q plus G, because it's multiplied by the Coulomb potential that is has an inverse relationship with this model square. So this is the model generalized for each Q, G prime. We compute this single matrix element with this plasmon pole. Here I am showing the analytic continuation. So we have two parameters, the poles and the residue. And there are two main ways to obtain the parameters. One, so we need to impose some condition. One possible option is the F-sum rule that I'm showing here using the Johnson formulas. This is just a recipe for computing. Even if we don't know analytical expression of chi, there is a recipe for computing this integral as a function of the electronic density. The other method is an interpolation of the parameters. For this, we just need two frequency points. So Z, in this case, equals 0, and Z equal I omega p. So we are computing a frequency along the imaginary axis. And then with these two parameters, we can interpolate the model. This recipe is by Godby and Nitz.
Can we ask a question?
In the end, I prefer in the end. So here I am showing the comparison. So this is the polarizability computed for 3 different materials. So the panels on top correspond to the polarizability computing along the imaginary axis, where we get a smooth dependence because all the poles of the polarizability lies on the real axis. Then if we sample the polarizability along the imaginary axis, what we see is something like this, no? Very smooth. We see the main structure correspond to all the poles at the origin of coordinates. Then as we go far, we lose the information, no? But then, so I told you, we can compute one frequency at a time, the reduced polarizability, then interpolate the model, for instance, along the imaginary axis. But then, since we have an analytical model, we can evaluate the model on the real axis, where actually we want to compute the self-energy. And this is the comparison with the full frequency case. So here in this Dyson equation, what happens is all the poles of the K node that are single particle are overlapped, and we get this overall structure. So we have this for silicon. It's very, very simple to see that we have a plasmon, and it's not always like this. No, we have more complex material, but in the end we have our overall structure. So this is a table from this paper I am taking for comparing different plasmon pole results of the band gap in this set of materials. So here, beside the Hybertsen, Louis, and Godby-Nitz recipe, there are more refining of the plasmon pole model by von der Linder, Horch, and Engel Farid. They use all the same Johnson rule, but the refinement lies in the spatial coordinates. So we also have understood this Johnson rule that can be written as in the form of this limit here. Then we can rewrite Hybertsen and Louis equation for the plasmon pole in the similar way of the Godby-Nitz version with an interpolation of 2 frequencies, and the second one is at infinite. So just to say that the sampling is a general procedure. So as I showed before, the plasmon pole provides quasi-particle with a energy with a reasonable level of accuracy in many materials, but it has several limitations. The first one is that we are not able to describe the imaginary part of W. So this results in the representability issues in the self-energy. This is the self-energy of aluminum. As a simple case, we can see that the self-energy has a very well-defined peak full frequency, but here so in the self-energy, we have a summation over the state that results in this, all these peaks, the discretization of all these peaks in the plasma pole case, because W doesn't have the imaginary part well described in the plasma pole model. So if we compute quasi-particle around the Fermi energy, we will get very accurate result compared to full frequency. But as we go far from the Fermi level, we will reach a region very noisy, and we will get some problem in the plasma pole model. And also, there are materials with the self-energy is more complex, has more frequency, more structure in frequency, and the plasma pole is expected to fail in these cases. So, regarding the integration of the self-energy, we can see that we can use the plasma pole. So we have an analytical model for W that is simple to integrate the convolution in the self-energy. But there are also alternatives that are called full frequency. The first simple example are if we can integrate sigma in the convenient basis set, or to use a spectral representation. But these approaches are usually accompanied by some approximation. For instance, we can approximate the polarizability metrics as almost diagonal. So the integration is exact in this basis set, but there may be some approximation. So this also may be system dependent because, for instance, we use a localized system. We can use localized basis set in order to get a few, the less number of the basis set to be as small as possible, because the computational costs explode with the size of the system. There are also numerical integration method. For instance, by using quadrature rules. For this, we need to compute the integral numerically in a very fine frequency grid. This is the real axis scheme implemented in Yambo. Or we can use the full frequency contour deformation or the analytic continuation through with some models, for instance, analytical models like the Padre approximation. Then this list is not meant to be a comprehensive list. There are many more methods. For instance, we can use the Fourier transform to imaginary time, or some stochastic approaches to compute the integral. But we also add our new development is also an analytical model that we call multipole approximation. So I will explain now the main approaches implemented in Yambo. So the plasma pole, the full frequency on the real axis. I will also explain the contour deformation because it's a very used technique, and then the multipole approach. So if we substitute the green function in the self-energy integration, we get this expression. We can simplify, so we can reduce the limit of the integration if we use the symmetry property of W. So that W is antisymmetric. Then this integral can be computed using quadrature rules. I am listing some of the possibilities here that are compared in this paper. Here, so the version implemented in Yambo is called piecewise linear. So what we do is to approximate W linearly in each interval that we are computing in the very fine frequency grid. So this approximation is better as we use a finite mesh. So since then we approximate W linearly in each interval, and since we have now an analytical expression of W, we can integrate the self-energy, and we get this expression over here that is the one implemented in Yambo. Then, in order to understand the computational cost of this approach, we need to analyze the pole structure of the GW operators. So the green function has 4 poles on the excitation energy, Kohn-Sham if you use G naught, W naught, while W, so chi naught have poles in the transition energy, then this pulse enters in the polarizability, but the Lehmann representation is general. So the polarizability also has a Lehmann representation, just that we don't know where are the poles. But W also have this pole structure in the complex frequency plane. Then, so in order to represent these objects, we need to use, because we cannot put an infinitesimal imaginary part in a computer, we need to use a finite damping parameter, and we can interpret this in 2 different ways, but are equivalent. So either we interpret like the poles to have a finite imaginary part. This corresponds to broaden the pole, so we don't have delta-like peaks anymore. They have a small broadening. Or we can interpret as the imaginary part goes to the frequency in which we are evaluating the operators. So in this sense, we can think of as a time-ordered real axis due to the sign of the imaginary part, like I'm showing here. So in this sense, we can say that the pulse lies actually on the real axis, and this is why we have the name of full frequency on the real axis. But in the end, we need to use a finite damping in order to represent this object. So as if we use a very small number damping, we need to use more frequency to represent these delta-like peaks. This is a parameter also in the code. Then, also in this work, it can be shown that, so if we go to the frequency plane, the complex plane in general, we close a contour, semicircular contour on the upper semi-plane, we will englobe the same pole as if I use a contour like this, the semicircular in the left side of the plot. So with this, we can transform an integral on the real axis in an integral along the imaginary axis. And this is one of the first idea of the contour deformation technique. So in the general situation, we have a convolution. Then the general situation, the frequency in which we want to compute the self-energy is not 0. Then there is a shift of the poles of G with respect to W. So as you can see here in this plot, it's very complex, but this is a semiconductor because I have a gap, but in general, so these black points are the poles of W, while the crosses are the pole of G, evaluating omega minus omega prime. So in the case of this omega is 0, they are aligned with respect to the imaginary axis. But in general, they are not. Then there are 2 different formalities to integrate the self-energy using this kind of techniques. One is called imaginary path axis integration, that is using the Keldy formalism in order to define this kind of contour. So it's the same idea. An integral on the imaginary axis can be transformed into an integral. An integral on the real axis can be transformed in an integral along the imaginary axis. I am in the dashed line represent the closure of the contour in order to englobe the same poles as I rotate the contour to get the integration along the real axis. Then there also we can also use the residue theorem and to perform a contour like a Lehmann scale that is represented here. But in the end, these 2 approaches are equivalent. Just you will find different names in the literature, but in the end, we are including the same poles within the contour. So the final expression, if you use the residue theorem, is that the integration on the real axis is equal the integration along the imaginary axis plus the sum of residues entering in the contour. So in order to, so it may seem that we did nothing, but as I showed you before, the dependence, the frequency dependence along the imaginary axis is much more simpler than on the real axis. Then, in order to solve the integral along the imaginary axis, we can use, for instance, numerical evaluation using similar quadrature rules. But then the mesh will be, so the number of frequencies that we need to use in order to convert this integral would be much less than if we do it on the real axis. So we could use also interpolation, fit models, or the analytic continuation technique that I will explain in a second. So since this dependence is very simple, we can use a simple form to interpolate this, and then we can do two different things. Either we use this equation here, compute the integral analytically with one of these two analytical forms, or we use directly the analytic continuation of the self-energy. That is, we compute the self-energy in the complex plane in general with these two analytical forms, and then, like in the plasma pole, since we have an analytical form, we can evaluate it on the real axis without the need of compute the residues. This is the origin of the two different names. Either we use the contour deformation, we have the summation of the residues. This is more robust, or we use an analytical model for the self-energy in order to just evaluate the self-energy on the real axis with this model. Then I will explain our approach that we call multipole approximation. You can see it as an extension of the multipole model. Here we model the polarizability with a finite number of poles. So again, this is inspired by the Lehmann representation, but here the difference is that we don't want to use a very large number of poles. So these poles in general are allowed to be complex in general. Then the idea is that we are passing from a single particle picture where we have a lot of transition, like in the kind of the polarizability at the independent particle level, to another picture in which we want to reduce the number of poles. So what we want to describe are collective excitation of the system. Then there is the way to use reduce the number of poles by allowing the poles to have a finite imaginary part. The way of obtaining the parameter is by an interpolation procedure. In this case, we need to use a number of frequencies that is twice the number of poles. And this leads to a nonlinear system of equations that we can solve with two different approaches. One is a mapping into an equivalent linear system, and the other is based on the Padet-Tillis iterative procedure to solve Padet approximation, because this multiple model can be written as a particular Padet approximation. Then the key point of our approach is to choose how to choose the frequency we want to use in the interpolation. We have studied several combinations, and we have proposed this recipe that we call double parallel sampling. Here in this plot, I am showing isolite corresponding to a toy polarizability that has 200 poles on the real axis. And the idea of this sampling that has two branches, one closest to the real axis and another one further away, is that the blue line introduces a simplification because we are far from the real axis. What we see there is more smooth than what we get on the real axis. But then we also add points close to the region we actually want to compute the self-energy, and somehow this combination is optimal. So the details can be found in our paper, but with around 10 poles, let's say, is enough to get a very accurate description, as I will show later. We also use a failure condition in order to avoid unphysical position of the pole. This is already present in the plasma pole model. In the Gottvinitz implementation, if this condition is satisfied, we usually fix the pole to a constant value of 1 We have generalized and improved this condition in the multiple case. Then we have we propose two quantities to monitor the interpolation. One is the number of failures in the whole matrix, and the relative standard deviation of the model with respect to the sampling points. We can see here these two quantities, the average in the matrix as a function of the number of poles, also compared with the plasma pole case. For these three materials, as you can see, there may be a very large number of failures already in the plasma pole. That is close to 40% in the case of TiO2. The multipole with one pole, even if we are fixing the same number of poles, the error is lower because we have changed the condition. But in general, both quantities go to zero as we increase the number of poles. Then this is how looks the polarizability one random matrix element. In the case of HBN, computed with different number of poles and compared to the full frequency case. And we can see that 8 poles is already very good. So here I show different matrix element of HBN. So we are using the same number of poles for all of them. We can describe real and imaginary part of the polarizability at the same time, and work for diagonal and non-diagonal matrix element in general. This is the case of silicon. That is more simple. So the first element, that is the most important one, looks like a single pole. Then there is also TiO2 that is more complex, but the multiple with a small number of poles managed to get the overall description. So some elements are more complex, but as I mentioned before, for larger G, this element is less important. So you can see on top the scale, so compared to the first element. So in the end, we get a very good description. So then we can compare the result of the quasi-particle with these three different approaches: plasma pole, full frequency, and multipole. I am using the linearized quasi-particle equation, as I show here. And this is the comparison. This is the difference between the full frequency gap, the gap computed with full frequency, and the multipole case, and also compared to the plasma pole for the three materials. We can see with around 10 poles, we get very accurate results with comparing to full frequency results. Then the multipole model also provides an analytical form for the self-energy. So simply, this is the integral. This is an extension of the plasma pole case. So we have the green function. We have a multiple analytical model for W, and then we can integrate the self-energy, and we get this expression that we can test against full frequency. This is the comparison for the silicon case. So here we have two quasi-particles corresponding to the gap of silicon, computed with three different approaches: plasma pole in blue and gray, full frequency in red and orange, and the multipole with 8 poles in black and gray. So we can see that the multipole provides a very good description of the whole energy range relevant for both the self-energy and the spectral function. So as a summary, I show you there are several methodologies addressing the full frequency dependency in the ideal approximation. We need to be careful to decide which is better for the system we are studying. There are three main approaches in the Yambo code. One is the plasma pole that uses two frequencies. So we have one pole. We need two frequencies. The number of frequencies is proportional to the computational cost. In the real axis approach, we need at least 100 frequencies. Depending on the material, for TiO2, for instance, I have used 1,500 frequencies. And this can be compared to a simple multipole model where we use around 10 poles that correspond to 20 frequencies. So in the end, the multipole, I have shown that the multipole with an optimal sampling provides a very accurate description compared to full frequency method and much lower cost. So this is the bibliography I have used for the present presentation. So the first book is just for introduction DFT. I like it. I use it for my thesis. This is the same books that have been shown before. And these two are the Yambo papers. And if you want to take a follow-up of my presentation, you can go to the paper I already posted several times or to my PhD thesis. With that, I thank you very much for your attention.
So the session is open for questions, if you have any. Yes?
Yeah, it's just a curiosity. You said that in order to improve the plasma pole approximation, the first simple thing you can do is to start to considering the reciprocal lattice structure of the plasmons. So you start putting plasmons with Q, G, and G prime.
Yes.
Yes. I was wondering, what's the meaning of plasmon poles with the G different with G prime?
So the energy of the plasmon dispersed with Q.
Yeah. Okay. Yeah. No, but with if there are reciprocal lattice vectors different, G different from G prime.
So yes, you have a model. So you see this picture. Let me take silicon. So you have a whole matrix, no?
Yeah, no, but in the multipole, I understand, but okay.
So what the structure of the polarizability is like the head of the polarizability looks like a single peak for many materials. Then this the amplitude diminishes, but then we have more structure correspond to, because we have all the possible transition, no? And we have less overlapping in this matrix element, but the amplitude is diminishing. So the idea of the generalized plasmon pole is to approximate all the matrix elements. So not only G prime, this is for Q equals 0. For different Qs, we use the same model. So we have two parameters for each matrix element, G prime, Q. And it's less accurate for other matrix element, non-diagonal, etc. But also the amplitudes diminished. The idea is to use the same model for all the matrix elements.
Just I try to reformulate. I think his question is, if I got it right, why do we have a pole which depends on G? So I think he's no. On G and G prime.
Yeah.
So because so you're asking why do we have omega G prime Q? This is your question?
Yeah, but only for the plasma.
Oh, yeah, only for the plasma. Yeah, the plasmon pole. But, so maybe Dario, you can comment on that.
Okay. So yes, because if using, so you need to take into account non-homogeneous materials.
I think the pole is not dependent on G and G prime.
No. The poles, no. Sorry. This is the expression of the polarizability, the full expression. So you can see here that the poles do not depend on G prime.
It's the same pole. It's just the residuals which are changing, and then you see
yes.
in the frequency plot that
the residues are here in the numerator, depend on G prime. But then the idea of the generalized plasmon pole is to allow, since we will use one single pole, let's allow it to be different for all the matrix elements. So you use a model, but is somehow flexible, no? And the multipole approach uses the same idea. So we have 10 poles that are different for each matrix element.
Okay, so another question from here.
Sorry, I go very basic. I think you went well, like a lot in the specifics, but maybe you can argue of like the reason behind why you have this structure on the screen interaction. So like, which is I guess is the region of the plasma pole approximation. So why do you have these divergences? So can you give like a physical intuition behind it? And is it valid only like in molecules, or it's only valid on solids? Or
Okay. So in general, so this chi naught is at the level of non-interacting particles. So as Andrea Marini was explaining, in the end, if you consider the screening, we have collective excitation. The main contribution to this screening potential are plasmon. So our collective excitation. Of the material, no? The response, how the material responds to a perturbation that is removing or adding an electron. This is a collective excitation. You don't have a single particle picture anymore. So, and mathematically, this is reflected in the Dyson equation. So, this is a nonlinear equation. You start with this kind of representation for each matrix element. So here you have several matrix elements. You have a polarizability that have delta-like peaks in all the possible transition, single particle transition. But then when this object enters in the Dyson equation, you have a superposition of all these poles that changing, let's say, the residue. So in somehow you have an envelope of all the transitions, and you get an overall behavior that looks like one peak, very big peak that corresponds to a plasmon.
So if I can comment on that. So, I mean, what you're asking is why do we have different structures in between the macroscopic, the head of the response function, and the microscopic terms? I think that in general, the common knowledge is we know that the macroscopic screening has this big plasmon pole, and this is what is used as an input for the plasmon pole. But we don't know what happens to the microscopic screening. And what he has shown is that at the microscopic level, the response can be different. So you can have the poles which are shifted and even multiples. I would say that so the microscopic screening is a bit different from the macroscopic one. And then if you think to a molecule, for example, a big molecule, the macroscopic screening tends to go to 0 because you are in vacuum, but there is a microscopic screening, which is important. Yeah.
Okay, yes, I forgot to answer that part of the question. So you can use the plasmon pole model for any kind of materials. But let's say it's better for, doesn't depend on the dimensionality. So there are some cases like Marine have studied with the strong screening interaction. This means very complex frequency structure that you cannot approximate with one single pole. So the deviation would be larger in this kind. The example are metals with low plasmon energies. So if we have this main structure very close to the origin of coordinates, this will result in poles. So let me try to explain. This object enters in the self-energy, and you will get the poles will be entered here. So if you have in the polarizability a pole close to the origin of coordinates, this will result in a pole close to the Fermi energy. And then the speech I made before that the plasma pole is good if you are in the tail of the polarizability. So in the tail of the self-energy, it's not valid anymore because we have a structure close to the Fermi level. So whenever you find a material that have structure in the polarizability close to the origin of coordinates, it could be a candidate for not using the plasma pole.
Okay, I think it's time to move to the next speaker. We thank Dario again.
Ci sono cose col microfono così da tenere.